lifesaver for what's it called? Integration by parts. Jim Voss was like, yeah, that's not.
Okay.
So we're just gonna guess and check.
Think of it as like coffee in the octane.
So are there any questions on the homework?
Currently.
Stops at 1.
I'll keep on with 8.2. So with integration by parts, you don't necessarily have to have two functions of x like we've seen so far. For instance, with the antiderivative of the natural log of x, we can integrate that by parts. So you can let u or dv just be the dx part. That's totally fine. And then this is how we're going to evaluate the antiderivative of the natural log of x. So we're going to identify our u and our dv. What should our u be? The natural log or the dx?
Natural.
Natural log, logarithms. Remember, if we let natural log be dv, we still have to find the integral or the antiderivative of dv. And we don't know, that's the whole point of doing this. So u is ln of x, dv is dx. Okay, so those are the two things you establish when you integrate by parts. Then we take the derivative of u. We get 1 over x dx. And the antiderivative of dv. Yeah.
X. Oh, you wrote it. I
Yeah,
thought you
never
were
know with
looking
me
for a
sometimes.
question there. I was looking down at my paper and I was like,
It's all good. Okay, so then we'll write it right here. The antiderivative of the natural log of x, dx, is equivalent to u times v minus the integral of v du, which is just going to be dx, or whatever, 1 dx, whatever you like. Okay?
Isn't it gonna have the little, oh yeah.
So we have x ln of x minus the antiderivative of dx again, which is just x. So there's the antiderivative for the natural log of x. Any questions on that? So you can have your u or your dv being just the differential part, dx, dt, whatever. Okay. So evaluating the number 7, e to the x cosine of x. There are instances we see in this example where, remember when we said you integrate by parts, that the integral of v du should be the easier, or it should be equivalent to the original. So we'll see here what happens is you keep getting the same sort of iterations of the functions, and the integral of v du never actually gets any simpler. And how we handle that is just by an algebraic technique. So e to the x cosine x, u should be cosine x. Yeah, if we're just trying to be consistent with our acronym, you could have your u being e to the x as well. Here it doesn't matter. Then dv is e to the x dx. Derivative of u with respect to x. Minus sine x dx, and antiderivative of dv gives us v equals to e to the x. Okay. You have the one in your homework, kind of like this, was similar to something to the effect e to the 7x times cosine of 3x. It's the same sort of approach. You just have these constants that keep changing, and they're sort of a pain to keep track of. So let's write out the integral of e to the x cosine x dx is u times v minus the integral of v dt. Again, I would keep the signs, you know, kind of establish everything and then try to reconcile the signs. You know, the more things you have involved, like with this e to the 7x cosine 3x, the more things involved, the greater the tendency is to forget a negative when it should actually be there. But since we do have minus the integral of minus e to the x, then put that in, we can clearly see that this should be positive. And so at that point, we'll change it. Do whatever works for you, but that's what I recommend. All right, so then we've got a similar thing. You know, we see like this round of synthetic, or what are we calling this? Integration by parts. It didn't quite improve because we still have the exponential times the trig function. So we're kind of stuck here. We're going to go one more time and see what happens. Technically, you should pick a different variable. We've already used u, so I don't know, use s or t or u bar or whatever. I'm going to let that be sine, and dv again, e to the x dx. Take the derivative of u bar, so you get cosine x dx. Try to remember your differentials, your dx's with your dv's and your du's. And v bar, again, is e to the x. So I'm going to write this out again. This factor stays the same, plus the integral. We're going to change the integral now into these two pieces, u bar times v bar, so e to the x sine x, minus the integral of v r du bar, e to the x cosine x dx. Any questions on where we're at? So again, this step we see still have an exponential times the trig function, but with this step we have the same integral on both sides. So just an algebraic technique, you've got two of the same quantities over here. We're going to combine those quantities together and solve for that quantity. So from this point, we're going to add this integral to both sides. Because otherwise we just keep going and just keep going forever without any reconciliation. So we're just going to add that to both sides and have two of those integrals over here. Equaling, what do we have? This e to the x cosine plus e to the x times sine. You know, being a little, we're just, I kind of being sloppy with the constants. We'll just put it in at the end. So all we need to do is solve for that integral and divide everything by 2. So that gives us that the antiderivative of e to the x cosine x is all of this stuff over 2, or times 1/2. Like that, or we could even take the e to the x out and just say it's 1/2 e to the x times cosine plus sine. And then we can put our c in again. So that's the technique there. If you keep, especially with like exponentials and trig functions, there's other instances where you could use this too. But the key is to recognize that you have the integral you're trying to figure out, and that same integral on the other side of the equation. That's when you would do this. So with the one that's in the homework with the constants like 7x and 3x, you might have some goofy thing over here, like you might have like 37/16 of that integral. Once you combine them, you just solve for it the same way, just the numbers are a little funky. Okay. Are there any questions on that? So, a situation like this, if you're using that tabular integration, it's not gonna tell you when to stop. Like when we integrated like x squared times e to the x, we kind of knew when to stop because the derivative of x squared eventually reached 0. So if we say, all right, well, originally my u was cosine x, and my dv was e to the x. Derivatives here, we'll just space them out. We just keep taking derivatives, right? It's always like a form of sine or cosine. It never really zeroes out, so it's not clear as to where you should stop. I think doing it the long way, how we just did it, will give us some insight onto things that don't have like a zero derivative eventually, like when you should stop. Okay, and then e to the x. E to the x.
So if you know something's going to be repeating, do you suggest usually stopping after 2?
It may be 2, maybe, I don't know. Just depends.
Okay.
It really depends. Here, yeah, 2. Remember, you start off, this is positive, then alternate negative, positive, negative, positive, so on. And then we cross cosine times e to the x. I have enough space here. Cross, we've got a negative sign times e to the x. Remember, this is all of this work is to show what this antiderivative is. Okay, and then we cross again. We have negative cosine e to the x, but we know that's that stuff isn't there, right? So you got to recognize that if I do this, then it's not correct. And I think honestly, without doing the integration by parts the long way, if you will, like it's not really clear. But what we did mention last time, when we're crossing, there is no integral in front. But when we move horizontally from here to here, we integrate that thing whenever we move horizontally. So we have minus the integral of those two things. And that's it. You really just have to know when to stop. So I think there are some limitations to tabular integration, even though it's in many instances really efficient. You still got to know what you're doing. Any questions about that?
So if you do the tabular integration method, like you said, when you just multiply horizontal, you get that integration. You're just looking for the original expression.
Right.
Within that. Okay.
Yeah. So with these types of things, now that we've seen it, we know, right? You're just looking for the original expression. It's not going to be this first line because the first round of integration by parts. I mean, you wouldn't even use integration by parts if you're not going to go once at least, right? So we recognize that if I went across right here, well, I haven't even integrated by parts, but I've moved across, so I would say that this is equivalent to this. Okay, well, it doesn't give me any information because that's what I started with. So I'm going to cross here, and then when I look horizontally at this line, I say, well, this product is the same thing that I started with. So I need to move across, integrate that, combine line terms, and solve. Yeah, I don't. Does that make sense? You're just looking for something past the first row that is the same product of the functions you started with. Yeah.
Would it have to be the opposite, though? So if it's positive on one, it'd have to be negative on the other. Otherwise, you'd end up with 0 on one side
Yeah.
of the equation.
Yeah. Otherwise, if this were a negative here, then we would have both things on the same side, and then they would just zero out, right? You just have this integral over here, and the same thing on the other side. Whatever, and then you have this as well. So if you subtract, you get a false statement, right? We would say 0, we've got 0 of these, is e to the x sine x times, or plus e to the x cosine x. Doesn't make sense. So they don't necessarily have to be opposite as they are here because, sometimes when you've got coefficients next to these x's, you might end up with one of them over here, like you might end up with, I don't know, one of these over here, whatever this is, and I don't know, like 3/2 of them over here. Even that were negative 3/2 or whatever, you're just basically looking for the same, integrand expression, yeah. If it happens that they're the same sign, like if this happened to be a positive cosine, and you did that, then more than likely you've done something incorrectly, because you shouldn't get 0 is equal to a sum function. But yeah, I mean, so with all those little things you got to pay attention to. Certainly, some cases pose limitations, I think. All right, any other questions or comments there? So we'll see there's these reduction formulas for specific functions and their powers. We see reduction formulas in 8.3 as well with powers of trig functions. I'm not going to have you remember the reduction formulas, so don't worry about memorizing these things. But the reduction formula for powers of x times e to the x, in order to verify that the formula is true, we're just going to integrate by parts. And u is x to the n, our algebraic. dv is e to the x dx. So derivative of u with respect to x is n times x to the n minus 1 dx, and v is e to the x. So, with one application of integration by parts to that, we obtain this reduction formula. So that's why I think it's easier to know integration by parts. 1, because you're going to be tested over it, and 2, it immediately gives you the formula for this. So this integral x to the n e to the x dx is u times v minus the integral of v times du. So that's the formula, you verified it. The only difference is they've taken this constant and put it out front. So even if you did the reduction formula or knew it, you still have to evaluate this integral, right? Because the integral is in the formula. There's no way around it. You could use the reduction formula again on this integral and keep doing that until you have just like the integral of e to the x. Because eventually the x to the powers will vanish. But, you know, for whatever that's worth, there's no need to remember that reduction formula. Okay. Just to see how that works, we're going to use that reduction formula for x cubed e to the x. So it says that, right here, that's equivalent to x to the n, where n is equal to 3. X cubed times e to the x minus the integral. We have n out front if we want, so that's our n. Times x to the n minus 1, e to the x dx. And then we apply that, apply the reduction formula again to this integral right here. And so on and so forth. So this time n is equal to 2. And we just rinse and repeat. We have x to the n e to the x, or x squared e to the x, minus 2 times the integral of x e to the x. And then you apply the reduction formula once more to this thing right here. So I think, I don't know, personally before I did that, I would just sort of clean this up a little bit. And just apply the reduction formula to this thing. So now that's n equals 1. That tells us it's going to turn into, or the reduction formula says that that's x to the n e to the x minus the integral of n times x to the 0. So in this last one here, we're just integrating e to the x. Which finally, that integral, you don't need a reduction formula to do, so. It's kind of how it works. You're just repeated use of integration by parts. Does that make sense? Again, there's no need to memorize that. If you do this integration by parts, you know, through each iteration, you're probably losing a total of like 10 seconds identifying u and dv. So, I guess we can finish this out. And then for something like this, the tabular integration is much faster anyways. questions on that? Integration by parts for definite integrals. So this is what they're more or less what they're showing in the textbook as well. But that first one doesn't involve an integral. It's still evaluated from A to B. So I don't know if you want to keep track of that, that's fine. But usually, what I prefer to do is just to find the antiderivative fully, and then just plug in the bounds for all into all of that. If you want to carry the bounds on the function uv, and then figure out the antiderivative of v du, feel free to do that. But we're just going to find the antiderivative first, and then apply the bounds once we're completely done. So we're going to do this first. Now again, typically candidates for integration by parts involve two functions of x multiplied by each other. So, that's kind of what we're keeping in mind when we're, trying to determine which integration strategy to use. We have two functions of x. We're going to try integration by parts. So our algebraic for u, or exponential for dv. Derivative of u is 1. Antiderivative of dv. So then the antiderivative here is, I guess we'll write it as 1 over 9 times x times e to the 9x minus the integral of 1 over 9 e to the 9x dx. uv minus the integral of v du. We can take the antiderivative of 1 over 9 e to the 9x now, so we will do that. Minus, so we get 1 over 9 times 9 e to the, excuse me, e to the 9x. Now, we're keeping in mind that we're going to evaluate this from 0 to 2, so we don't need that constant in there. We just need the antiderivative function, and then we'll evaluate this from 0 to 2. I'll just rewrite it. Our antiderivative evaluated from 0 to 2. I mean, technically the 0 to 2, after we've done this u times v, technically the 0 to 2 is here, but once you get here, it's here as well. It's stuck here. And after you find the integral, it's here as well. Whatever's going on with that. Okay, it's there. So no, I just think that's a lot to have to keep track of. So just find if you want, find the antiderivative first, and then plug in the bounds. Okay. Any questions on that? So yeah, that's final answer, 17 over 81, e to the 18, plus 1 over 81. Anybody have any questions on that? Is it reasonable? Okay. So like I said, with integration by parts, you can now integrate the inverse trig functions. So if it was just the inverse sine of x, inverse tangent, whatever, like all of those can be evaluated by using integration by parts. So with that acronym, U should be the inverse trig function, and then dv would just be the dx when you do these inverse trig functions. So we're going to look at z inverse secant of z, evaluated from 2 over root 3 to 2. So again, we've got a product of two functions. Integration by parts is probably the likely solution. So what should our u be? Inverse secant. And then dv is z dz. So then we've got to remember to find du, which entails us remembering what the derivative of inverse secant was. Does anybody remember? It wasn't like super common, I don't think.
Was it the one with x first on the bottom?
Uh-huh.
Oh, okay.
Yeah.
1 over absolute value of x, square root, and I don't know. It's either a squared minus x squared or like x squared minus a squared. But
Yeah,
I don't
well,
want to confuse anyone, so.
Well, you did good. Anybody remember what's under the radical?
X squared minus 1.
Yeah. It's the
Yeah, exactly.
z squared minus 1.
Ah.
But, you know, there's an absolute value there. If we don't have to deal with it, let's not deal with it. And really what helps us identify whether we need that or not is just the region we're in. We're from 2 over root 3 to 2, and that's always positive in that region, right? So we're going off, we're basing this off of the bounds. Z is in. Sometimes they use a fancy E like that to mean that it's Z is an element of. So if you ever see, I don't know if you've ever seen that, but that's what we'll use. Easy to write and stuff. So Z is a member of the interval 2 over root 3 to 2. That means Z is larger than 0. So we don't need the absolute value. So just for ease of working with this thing, we'll just say this is the derivative of inverse secant in that region. All right, that'll help a lot. V is the antiderivative of z. Z squared over 2. I put this line through the z because my 2's and z's look similar sometimes. Sorry. du is 1 over z root z squared minus 1 dz. Again, we're finding the antiderivative first, and then we'll worry about the balance once we have the antiderivative. U times v, we have z squared over 2. Sorry, I'll try to make it more clear. 2's. Inverse secant of z, u times v, we have minus the integral of v du. So we'll simplify this integrand here on our integral. We can cancel out one of the z's with this z, and then we'll move, if you want, I'm going to move the constant 1/2 out front as well. Z over root. That's what we have. Of course, you could simplify before you actually plugged in. It doesn't really matter to me. Okay, that's where we're at. Do y'all have any questions so far? Okay, so then how are we going to integrate the z over root z squared minus 1?
Use of.
Yeah, I'll use substitution. Or whatever, a t substitution. We've already used u, so what else do y'all like after u? Anybody?
U bar.
All right, let's do with that. So what are we going to let u bar equal?
Z squared minus 1.
Z squared minus 1. Okay. See if that works. Then du bar 2z dz. Or 1/2 du bar. All right, so it'll work. dz times z, that's going to be accounted for by 1/2 du bar. And then the bottom is just going to be the square root of u. So we're going to have the square root of u to the -1 times that 1/2. So let's write this over here. We've got this. Minus this 1/2. Then we have that 1/2 times the integral. I guess we'll just put that as 1. Put this right here, right? How's that look? So there's, again, our 1/2 dz, that's our z times dz right there. Okay, so let's just call that u to the -1/2. Sorry, du, not dz. Everybody okay with that? So then we need to figure out what this is, resubstitute our expression for z, then evaluate that from our bounds, whatever we have. Okay, antiderivative is u to the 1/2 over 1/2. U bar, sorry. So antiderivative is 2 u bar to the 1/2. Okay, combine the constants. U was z squared minus 1. U bar, rather. All right. So quite lengthy, but nonetheless, we're here with our antiderivative at this point. Yeah, plus c. Remember your plus c. You're gonna put your. We're gonna evaluate in our bounds, so you can have c whatever to whatever you want. But yeah, there is the antiderivative. Does anyone have any questions?
Can you never put a z on a test? Never put a z on a test.
Would I ever?
Please don't.
Oh.
I'm changing it to X, just so you know.
Huh?
If you do, I'm changing it to X.
That's fine.
An inverse secant test either. That
Okay.
would not be nice.
Everybody loves the inverse trig functions, right? So we'll go
This whole
back.
time I kept mixing up my z's with two.
Arcs. Z worst.
All right, so we have the antiderivative. They both have a half, so let's take that out. All right, so evaluate our antiderivative we just found from those bounds. So we have 2 squared times the inverse secant of 2 minus 2 squared minus 1 to the 1/2. So there's f of antiderivative at the upper bound. We subtract off our antiderivative at the lower bound. So 2 over root 3 squared times inverse secant of 2 over root 3 minus 2 over root 3 squared, which would give 4/3 minus 3/3 is 1/3 to the 1/2. There's f of a. So if evaluating inverse secant of 2 and inverse secant of 2 over root 3, how do we evaluate those without our calculators?
Unit circle. Just use the unit circle,
Unit circle?
right?
You could, yeah. Secant, inverse, secant, reciprocal of cosine. Inverse secant, though, isn't the reciprocal of inverse cosine, right? It only works for their arguments, not the whole thing. So the inverse secant of 2 is the same thing as the inverse cosine of 1/2. Inverse secant of 2 over root 3 is the same thing as the inverse cosine of root 3 over 2. So what angle gives us a cosine of 1/2?
Power of 3.
Pi over 3, yes. Cosine of pi over 4 would give us 1 over root 2.
Okay, it's already 2 over 2.
Yeah,
The
it's
other-
already 2 over 2.
Like cosine's gonna be pi over 6.
Pi over 6, yeah. So cosine of pi over, oops. Cosine of pi over 3 is 1/2. So the inverse cosine of 1/2 is pi over 3. The cosine of pi over 6 is root 3 over 2. So the inverse cosine of root 3 over 2 is pi over 6. Yeah? So hopefully at least you remember that the inverse trig functions output an angle measure. Their input is a radian, or a length, if you will, a ratio. So if we take the cosine of both sides, then we see exactly how we're solving this equation. The cosine of inverse cosine is like the square of the square root. So we just have root 3 over 2, and then the cosine of this angle. So that's how we're thinking of it to answer this question. Cosine of what angle gives us root 3 over 2? Okay, so let's see what we have here. We have this 1/2 still. We have 4 pi over 3. Minus the square root of 3. We have 4/3 times pi over 6. So what is that? 2/3, 2 pi over 9. We'll just write that 2 pi over 9. Minus 1 over the square root of 3. All of that stuff times 1/2.
Do you want us to leave it like that? You want it all multiplied?
Yeah. Yeah. We're in Calc 2 now. We can keep going. The hard part's over. If you just like type that on your calculator, it'll probably give you like the final result. I don't know. Maybe.
But
it
you
will.
usually want exact answers though?
Yeah.
So the calculator will get that.
Yeah, exact values. So I mean, at this point, it's just kind of tedious. We have our 4 pi over 3 minus our 2 pi over 9. We have our negative root 3 plus 1 over root 3. So 5 pi over 9. We have negative 3 plus 1. We have negative 2 over root 3 times 2. 1 over negative 1 over root 3. Or, you know, if you don't like radicals in the bottom, minus root 3 over 3. So whichever. Any questions on that? So naturally, the more techniques for integration you get, sometimes it's a detriment to have so many choices, right? Like going into the supermarket and try to find shredded cheese, you got like 30 options. Which shredded cheese do I want? If you just had one shredded cheese to choose from, it's easy. Just get that one every time. If we just had one integration technique, use substitution, you're super limited on what we can do, but at least we know how to integrate stuff. The more of these techniques we get, it's almost like the more difficult integration gets, because integration by parts, does that work? Does this thing work? Does this thing work? Right? So, again, just keep that in mind when you're doing these. I know if you're in specific sections, you know which technique is expected of you to do, but with that being said, when you're looking at the homework, try to look at patterns, like, all the ones you integrate by parts, just kind of keep those in your head. Like, why did I integrate these by parts? Versus in the next section when we do trig substitution, like, why did I use trig substitution on all of these integrals? And so you start to get a little clearer picture in your head, at least of the compartments. Like, these kind of functions I integrated with parts, this kind of function I integrate with trig substitution. So you start to, build that bank in your mind as to which route to take. I think that's, yeah. So that's the end of this section. What happened there? Okay, next section, 8.3, trigonometric integrals. So there's many varieties of these. We're going to look at specific ones. By and large, these integrals here at 8.3 are just a U substitution. So it's not that we have to learn a new technique to find these integrals. We just have to know like the correct procedure to use in order to make those things into a U substitution. So that's kind of the idea. Like the even powers of sine and cosine, like integrating sine squared and cosine squared. We've done those hopefully a few times where we kind of remember. But those reduction identities are also used if you have like the integral of sine to the fourth, cosine to the eighth. Like we just keep repeatedly using those. So those show up again. Another common one is this one here. But hopefully you remember all this stuff. Before we actually get into the I guess the powers of sine and cosine, secant and tangent, we're going to look at the antiderivatives of all of the other trig functions that we don't have. Cosecant, secant, cosecant, secant, cotangent, and tangent. I think we've already talked about a couple of these, but we can revisit them now. We're going to write the integral of tangent as the integral of sine over cosine. Remember our logarithmic form, the derivative of the bottom is kind of up here because the derivative of cosine is negative sine. So if we have that negative sign up there, it would be in logarithmic form. If I'm going to multiply this by -1, I need to multiply again by -1. So what is this antiderivative here?
Minus natural
Okay, good. So that's minus, that red minus out front. Antiderivative there then is the natural log of the absolute value of the bottom function plus c. If that, if that logarithmic form is weird for you, you're just going to do a u substitution here. The u is the cosine, du is negative sine. You have negative du sine dx, antiderivative of 1 over u. This also is written, or sometimes written anyways, as the natural log of the absolute value of secant. So they're equivalent by properties of logarithms. This -1 is the power on cosine, so it's the natural log of, the positive natural log of the reciprocal of cosine, which is secant. So whichever one, doesn't matter, they're exactly the same. We've got a similar tactic here with cotangent. We're going to write that as cosine over sine. And this one, you don't really have to do anything fancy because the derivative of sine is cosine. So this one simply is the natural log of the absolute value of sine. So you need to know these. You need to know these like you know the antiderivative of cosine and the antiderivative of sine. If you don't remember that the antiderivative of cotangent is the natural log absolute value of sine, then you just go through the u substitution process and you can get there. But one way or the other, you need to know these four. Okay. A lot of these four especially, they show up heavily when we use trig substitution. So they do show back up. Secant and cosecant, the process of kind of getting them into the particular form are very similar, but I don't know that it's intuitive as to do the procedure. I don't think it's intuitive. When you see it sort of unfold, it's like, oh yeah, that makes total sense. But it really, it's a little bit harder to have to remember how to derive it, I think. So we're going to write this as the antiderivative of secant. And then we're going to multiply by a form of 1 in the form of secant x plus tangent x. So again, I don't know that that's immediately obvious why you should do that. However, when we multiply out the top, we have the antiderivative of secant squared plus secant tangent. I ran out of room. All over that secant tangent. So now maybe it makes a little bit more sense. What's the derivative of the bottom? What's the derivative of secant?
Secant x tangent x.
Close. There's no negative though.
Okay.
So the derivative of secant is secant tangent plus the derivative of tangent, which is secant squared. So now we have the derivative of the denominator is the numerator. So this is now in logarithmic form. So the antiderivative, what would that be?
Natural log of absolute value secant x plus tangent x.
Right, natural log of the absolute value of our denominator, secant x plus tangent x. Any questions? All right, a similar technique, we multiply cosecant by cosecant plus cotangent over cosecant plus cotangent to get in log form. It's the negative natural log absolute value of cosecant x plus cotangent x. So for sure know those four integrals. Or at least know how we derive them. I'll just write this here. So it's the same idea that you have cosecant squared plus cosecant cotangent on top. What's the derivative of the bottom part? What's the derivative of cosecant?
Negative cosecant x cotangent x?
Yeah, negative cosecant cotangent. So you have the cosecant cotangent, but it's not negative. Right? Derivative of cotangent is
Secant squared x.
negative cosecant squared. So you have the cosecant squared, but it's not negative. So that's what we do with like we did with the tangent. We said, all right, well, it'd be super awesome if the top's derivative were negative. I can make that negative if I put a negative out here, which is why this negative is right here. So either remember the integrals or remember how to get to them. Do y'all have any questions at this point? So everything else we look at in 8.3 will be a U substitution in disguise. We just have to configure the integrand in a specific way, depending on what kind of functions we're dealing with, before we're, seeing that direct U substitution. But we'll take a break and then continue this.
Medicine, not
So he's given like exactly half the effort.
Okay.
Yeah, exactly.
All right, so the procedures sort of listed out throughout these pages, but if you've got powers of sine and cosine, and sine is odd, so m is the power on sine. If sine is odd, you split off one sine. And basically you want to think about what the factor or the term you're splitting off, the factor I guess that you're splitting off, you want to put that with the dx, because that will give you sort of like your dv. It'll tell you what you want to let u equal to. And as we go through the next few examples, what we'll see is that if you've got powers of sine and cosine, and sine or cosine is odd, then that's the procedure. You just split off the odd sine or cosine. You write the remaining powers in terms of u. The remaining powers of sine here in this instance would be written in terms of the Pythagorean identities. And our u substitution is cosine. So we see an odd sine. We're going to just write this as sine squared.
Why not just do a straight u sub?
So what would u substitution be here?
Wouldn't you make u be sine? Oh, I guess then you get the same thing.
Yeah, so if u is sine, then du is cosine x dx. I mean, you don't have a cosine x here. So we have to like manipulate it in a specific way to get that u substitution. We've got an odd sign, so we're going to split off one sign and put it with our dx. And then, you know, you think of that, it's kind of like comparable to your dv when you do integration by parts. So if this is our dv, then we're thinking about, okay, well, our substitution then has to be u equals cosine, because the derivative of cosine is sine dx. So we're going to let u equal to cosine. And all of them work, the ones that we see in 8.3, they all work that way. Whatever you split off, it's kind of like your dv that tells you what your, or your du, that tells you what your u should be. And then if we're trying to substitute in for cosines, well, let's do du first. If we're trying to substitute in, we don't see a cosine, but we do have a sine squared, which we can rewrite in terms of its Pythagorean identity, 1 minus cosine squared. For sine, and then our sine x, the sign that we split off with the dx. So this is pretty much now, all of this is our du, with the exception of the negative. And then the 1 minus cosine squared is just 1 minus u squared. So we need that minus out here, and the sine x dx is turning into du. We still have this integral. 1 minus cosine squared is now 1 minus u squared. Any questions about that? So honestly, it wouldn't matter if you had combinations of powers of sines and cosines. You know, like if you had, we'll see some examples like this, but if we had like sine to the 10th, cosine to the 17th, the procedure is exactly the same. We see this thing is an odd power, whether sine or cosine is an odd power, that's the one you split off. So we're going to split off one cosine with our dx, our u is going to be sine, and then we're going to rewrite the other ones in terms of the Pythagorean identities. Okay, so that's how we manipulate this into a u substitution. We have minus, I guess we can leave the minus out if you want. Whatever, I guess we can keep track of our constants, but that's what we're dealing with. Just a u substitution problem in disguise. So we have minus u plus u cubed over 3 plus another constant, and then we resubstitute. What was u? U was cosine. And that's our final answer.
Does the negative not distribute to the plus?
Yeah, so the negative distributed to the constant number 1, and it made it another constant we're going to call c. Yeah, you could write minus c if you want. It's the same thing. Okay. So that's what we're looking for, powers of sines and cosines. Which one's odd? Split one of them off. use substitution and Pythagorean identities, that's it. Any questions on this? So whether they're by themselves, here's cosine cubed. Notice it's the same procedure, n is odd. That's the power on cosine. Split off the odd one, split off cosine, rewrite the resulting term in terms of sine using the Pythagorean identities, and then you use substitution as sine. So it's virtually, the procedure here is virtually identical. We have a cosine squared times our cosine, one of the factor of cosine that we split off, we put with our dx. So in all of these, the thing you split off, you put next to your dx, that's essentially du is what you're looking at when you do that. So if cosine x dx is du, then u should be sine. That way du can be that cosine x dx that we split off. So that's our du. We need everything else in terms of u, or sine of x. So we've got to rewrite cosine squared in terms of sine. So Pythagorean identities again. 1 minus sine squared. Oops, times cosine. That's just 1 minus u squared du. Which is u minus u cubed over 3. Sine x minus sine cubed over 3. Let's see. Any questions about this? Okay. Evaluate sine to the 4th times cosine to the 5th. So when we have powers of sine and cosine, we'll see what happens if we're just integrating like cosine to the 4th by itself or sine to the 4th by itself. But for these here, we say, well, sine's even, cosine's odd. Since cosine is odd, has an odd power, I'm going to just split one of those off and write it with the dx. So I'm going to say that this integral is sine to the 4th times cosine to the 4th times my cosine is split off cosine x dx, because cosine is odd. So once again, since it's cosine dx, that's like our du. We want our u to be sine of x. So u is sine. Du is cosine x dx. So let's put this in here. We've got the sine to the 4th taken care of. That's u to the 4th. We've got cosine x dx. That's du. What are we going to do with cosine to the 4th?
You're going to rewrite it as one, you just rewrite it and split up that squared to make it, but then that expression, I guess, if that makes any sense.
Yeah.
Yeah.
So we're just gonna rewrite this cosine to the fourth. We're gonna write that as cosine squared. Squared. Because we know cosine squared is 1 minus sine.
Could you have turned everything into cosine with those? Sine squared of x equals 1 minus cosine 2x over 2, and use both of those identities.
So, sorry, say that again. Turn which one?
So even like from the beginning,
Uh-huh.
after you split it off into sine to the fourth and cosine to the fourth,
Uh-huh.
couldn't you use the sine squared of x equals 1 minus cosine of 2x over 2? And that cosine squared of x equals 1 plus cosine 2x over 2?
Uh-huh.
And then you have everything in terms of cosine. And just square those.
Yeah, but then you have a polynomial here in cosine to the fourth, right? So it's really all of this stuff. Well, it's all of this stuff squared actually.
Yeah.
That's what sine of the fourth is. So you're gonna have to expand this out. Same thing with cosine of the fourth. You would have to expand all of that out. Then you got to multiply all of that together.
Just a lot more work.
Then you got to distribute the cosine in. So you're going to have this massive polynomial-esque thing in terms of powers of cosine. And not only would they be in terms of powers of cosine, but they'll be in terms of powers of cosine of 2. So I suppose you could do that. It's just not nearly as efficient. Yeah. But yeah, I mean, in theory, if we just had a bunch of powers of cosines
This is where my brain went initially.
separated by like addition and subtraction, then yeah, you can just integrate. Yeah, I mean, you for certain could try that. Okay, so we've got cosine squared written as 1 minus sine squared, but that quantity is being squared, so we need to make sure that this is still squared here. And then our cosine x dx. And then we're ready to plug in for the u and the du. Yeah.
If we had odd powers instead of even powers, could we raise it to like a half power? So if it was cosine to the third, couldn't we raise it to the 3/2? So cosine squared to the 3/2, would that work? Or
So, like, if it were, what do you think? Like, if, for example, the antiderivative of,
let's just say both the terms were odd.
like, sine cubed, cosine cubed. Okay, could we?
Yeah, how about, this is an idea I had.
Sure.
I don't know if it would work, but yeah, we take the sine, we'd have integral of sine squared x times cosine cubed x sine x. So that would be the term we get rid of.
Okay,
So yeah, we'd have a u equal cosine.
right.
Okay, in this case, you wouldn't have to do it. I'm trying to think if there is a case where you would raise it to like a 3.5 power, so you would get cosine squared or sine squared, and you use the Pythagorean identity. You don't have to raise it to an integer power, right? It could still work in one of these other forms.
Right, like, so, like in the integrand, like being a fractional power, or
Yeah.
your substitution.
Or maybe if it was sine, well, what if it was a sine? I'm not sure where I'm going with this, but because yeah, the particular form it said it had to be in was sine was raised to an odd power and cosine to any other power.
Uh-huh.
So if they were both even, would there? I guess yeah. So both even would satisfy either of those conditions. Would you be able to raise it to like a half power?
Like the whole integrand? Like if it were like this, would you be able to raise all of this to like a half power?
Not the whole thing, but when you're doing the substitution, like is there a way to force this method to work when you have like the wrong kind of power according to the
Oh, you mean
condition?
like split something up so that you have like the exponents adding together to give you the original
So you
power.
can use the Pythagorean substitution even if both the terms aren't on, like in the example
Yeah.
you're doing.
Yeah, I suppose in some instances that could work.
Okay.
I don't think we run into an instance where we have to look at it that way.
Okay.
When we have even powers of sines and cosines, what they say is rewrite either one, and then you'll end up with this polynomial in terms of sines or cosines.
Okay.
And then it says use the reduction formulas. So we're not gonna use the reduction formulas, so we're not gonna like do those by hand.
So in that case, would the method I'm suggesting be faster, or would that also just run into the same problems?
That I'm not sure about.
Okay.
Like it would probably just depend on what the powers you're dealing with are.
Okay.
But in an instance like this, even if we did have like fractional powers here,
Uh-huh.
it wouldn't matter because they're going to get turned into u's anyways.
Yeah.
When you have to start using the reduction formulas, though, it could get a bit messy.
Okay.
Okay. So then we've got, what do we have? We've got our sine to the fourth, that's u to the fourth. We've got our 1 minus sine squared, times cosine x dx was our du. Does that look okay? So, we've got a product of two functions of u. You could either try, maybe we could try integration by parts here, a product of two functions. Or we could just multiply these things out. So u to the fourth, and then just integrate powers of u, times 1 plus u to the fourth minus 2u squared du, and go about it that way as well. I didn't try by parts, so I'm not sure it'll work, but. So we have the antiderivative of u to the fourth plus u to the eighth minus 2u to the sixth. And then that's pretty straightforward from there. So really, that's what we're looking for. The even powers of sines and cosines we don't really look at because it involves reduction formulas and you're not required to remember those. So, what is it? Sine? Yeah, u is sine. Resubstitute u for sine. And of course, something like this, it's sort of a pain to check. Is the derivative of this actually sine to the fourth, cosine to the fifth? It's not as straightforward with like some algebraic functions, but in theory, we can still check, is that right? Let's take its derivative to see what it is. Any questions there? Sines and cosines, you're looking for the one that's odd. You're splitting that off. That's telling you what your u substitution should be. The other portion is we're rewriting that in terms of the Pythagorean identities. That's the gist. Okay. So if both m and n are even, that means we have even sine and cosine. Use half-angle identities to transform them into a polynomial of cosine 2x. Apply the preceding strategies for powers greater than 1 for cosine squared 2x, cosine cubed 2x, etc. So, you know, sort of a very, I guess, in-depth process when you have both of those showing up. As far as sine being even by itself, cosine being an even power by itself, we're going to use those identities on that first page that we haven't read here. You can just, if it's to the 4th, we'll use that identity twice. If it were to the 6th, we would use that identity 3 times, and so forth. So we're going to look at the antiderivative of sine to the 4th. And we're going to write this over here. The identities for sine squared. We're going to write that out so we remember. And we're writing then sine to the 4th as sine squared. Squared. And then sine squared as the identity says. So we actually have to multiply this out. We have to look at it as 1/2 squared. I don't know where we want to put that, if we want to leave it in. Times 1 minus cosine 2x quantity squared. dx. So then you want to expand that. Expand all of that stuff and get all of this stuff. So we can take the antiderivative of 1 fairly simply, antiderivative of cosine of 2x fairly simply. But the issue that arises once again is now that we have a cosine squared we have to integrate. So to integrate the cosine squared, we're going to use the identity again. So for this one, I'll just write it over here. So cosine squared of 2x, according to that identity, should be what? 1 plus cosine of
4x.
4x, yeah. It's always double this here. So then we got to turn cosine squared 2x into this thing right here. So we have 1/4 antiderivative of 1 plus cosine squared of 2x, which is actually 1/2 times 1 plus cosine of 4x. We have our minus 2 cosine 2x. So now we can integrate each term, or if distribute it, we'll just go ahead and distribute this 1/2 so we don't have a multiple set of parentheses. So now each term is, now we can find the antiderivative of each term. So if 1/4, the antiderivative of 1 with respect to x plus, I guess we could have added the 1 and the 1/2. We'll do it here. x over 2 plus, what's the antiderivative of cosine 4x over 2? Or 1/2 times the antiderivative of cosine 4x.
Cosine 4x. Cosine 4x.
Divided by,
4.
divided by 4, right? Times the 1/2?
Yeah. 1/8.
Yeah, but, right, the antiderivative of cosine though is sine. So sine 4x over 4 times the 1/2. Sine 4x over 8 minus 2 times the antiderivative of cosine 2x would be
Sine of 2x.
positive, negative.
Well, I'm doing mine in a different order.
Negative minus sine 2x for this one. What do y'all think? Yeah, it's minus 2 antiderivative of cosine 2x again, sine 2x over 2 times the negative 2 is negative 1 sine 2x. You know, and we have some constant coming out of this. So I don't know, call it C1, call it K, whatever you want to call it. If you left the 1/4 in, you might just call that constant times the 4th. I don't know. That's why I always think it's just easier to put in a constant at the end. With antiderivatives anyways. Okay, so how many of these do we have? Okay, that's basic idea. You can see, like, you know, by hand it's super tedious. If you had sine to the 8th, having to do this, 4 different times, it's quite a lot. We have 2 over 2, 3 over 2x, 3x over 8. We've got plus our sine of 4x over 32 minus sine 2x over 4. 1/4 times this constant, another constant. Same exact procedure for cosine to the 4th or whatever. Do y'all have any questions there on that one? Number 9, you've got cosine cubed 7x, sine to the negative 2 of 7x. What would we do here?
Would you move the sine to the bottom and try and get a tangent x? Or not the tangent?
Oh yeah, because we would have cosine cubed over sine squared.
So you have a cotangent times cosine.
So let's see what that does. If we rewrote it like this, then we have this. Then we have this. We have cosine squared over sine squared. Times cosine 7x dx. So we can totally do that, right? Nothing wrong with it. Is it helpful? Probably not.
You just get off cosine.
Yeah, so we see that the cosine's odd. That's all we need to know. We've got once with the sine or the cosine being odd, we're back to the same procedure we had initially. It doesn't matter what the other power is. One of them's odd, you split a factor of that off. This is odd. We're going to split, oh sorry, that's cosine. We're going to split that off and put it with our dx. So again, the thing we split off and stick with the dx, that's kind of like our du, so our u needs to be the sine of 7x. Du is what?
Cosine 7x?
Yeah, 7 cosine 7x, because of the derivative. Multiply. We don't have a 1/7 in our integral, so we'll put the we don't have a 7 cosine, we'll put the 1/7 with the du. So we got a means to account for the sine to the -2. That's just u to the -2. We've got this right here. That's going to be our 1/7 du. What about the cosine squared of 7x?
Your 1 minus sine squared.
Right. We're just going to use the Pythagorean identity for this one here. Okay. So that's our cosine squared. Again, we've got a means to account for the sine, -2 of 7x, and for the cosine of 7x dx. So now we can substitute 1 minus u squared for this one times u to the -2 times cosine 7x dx was our 1/7 du. So we'll put that 1/7 down. Is that all right? That makes sense? Anyone have any questions? A little bit different, some manipulation happening, but it's the exact same procedure. So at least there's some consistency there. So we have 1/7 antiderivative of u to the -2 minus u to the -2 times u to the -2. I think I said that wrong. Anyway, that's just one. Got then 1/7 u to the -2 antiderivative negative u to the -1 minus u, and we'll have some constant here getting multiplied by our 1/7. Okay, so just make sure, like, when you plug back in for u, you realize what we're talking about here. We're talking about u to the -1 power, or this is the reciprocal of u. There is some tendency for some confusion here because u was sine of 7x. So when we plug back in, it's the reciprocal. It's not just because that's a -1 power doesn't mean it's the inverse sine of 7x, right? It means the reciprocal here. So that's negative sine 7x to the -1. So I think, well, that's why a lot of people prefer arc sine, arc cosine, just to kind of avoid situations like that. Which is, it's fine. If you want to use arc sine, arc cosine for inverse, that's totally acceptable. We'll just put all this over 7. And we'll get rid of this right here. Okay, so you can leave it like that, or you could write it with the sign 7x on the bottom. Like that. Either way, not an inverse sign. So don't let those like weird powers throw you off. You're just really looking for an odd sine or an odd cosine. Everything else can be taken care of with the U substitution. Y'all have any questions on that one? Okay, so these reduction formulas, they're here just for your reference, but you don't need to remember these. I'm not going to test you over these or ask you these or anything. There's no need to remember. But just to know that they exist, they're there, using the reduction formula to evaluate, for instance, tangent cube. We'll say this is our n equals to 3. This one here. Say, all right, well, tangent cubed, the antiderivative of tangent cubed dx should be tangent squared over 2 minus the antiderivative of tangent to the power of minus 2, so tangent to the first or tangent. Okay, so according to the reduction formula, that's what we end up with. What's the antiderivative of tangent?
Secant squared.
That's the antiderivative of secant squared is tangent.
Secant x, tangent x.
The derivative? Antiderivative of tangent.
It's a natural log, absolute value of
Yeah,
I
there
have
you
it
go.
written.
Looking
Secant
back
x.
at that first page.
Secant x plus c.
Secant x.
secant x.
Natural log of sec. We had two representations really, but again, this is why you need to remember that if you're plugging through these reduction formulas, you're eventually with the secant, the power of secant, you're going to hit an integral that involves secant. With tangent, you hit an integral that involves tangent. You got to remember, I either know how to do this or I just know what it is, right? There's really no other technique. So we could either say that this is tangent squared over 2 plus the natural log absolute value of cosine x plus c, or we could say that's minus the natural log absolute value of secant. So either one is fine, because we had two representations for the antiderivative of tangent. Okay. All right, similar thing here for like 12 secant cubed. We could just go up to this reduction formula, n equals 3, multiply all that stuff by 12. You got to know what the antiderivative of secant is. Another way we could look at this, here, let's look at the antiderivative of just secant cubed, and then we'll multiply it all by 12. So some of these, instead of using reduction formulas, we could work out using different methods. Like secant cubed, we could rewrite as secant squared times secant. And this, some of this is probably not obvious why we would do this until you kind of start to see it come together. But illustrating the fact that I guess just antiderivatives are hard in general. There's multiple things that work sometimes. Okay. So if we write it as secant squared times secant, at this point we don't have powers of secant to utilize. So say, well, we do have two functions of x being multiplied. Let's let u equal something, and let's let dv equal something else. So generally we said let u equal the leftmost letter in that acronym. Both of these are trig functions, so it's kind of ambiguous as to which one we use, right? When we said let u equal the leftmost function in that acronym, that was also identifying sort of the converse of that was dv should be like the biggest part of your integrand that you know how to integrate. So with that in mind, would we want dv to be secant squared or secant? Keeping in mind that we have to find the antiderivative of dv. Yeah, secant squared, right? Because we know the antiderivative of that is what? Tangent. Okay, so dv was secant squared dx. That means du has to be secant. Derivative of secant is secant times tangent. So I guess at this point there's really no indication that this is even going to work out. We're just going to see what happens. Okay, so that is, we're going to rewrite the integral here, secant cubed. That's u times v. Minus the integral of v times du. So minus the integral of tangent squared, secant x. So maybe at this point it doesn't look all that much better. We traded a secant squared secant for a tangent squared secant. Keep in mind we've got secant cubed on the left-hand side. If I write tangent squared as secant squared minus 1, I have it times this secant right here. Notice what that's going to do. I'm going to have the antiderivative of a secant cubed on this side. I've got a secant cubed on this side. The other factor is, can I find the antiderivative of secant? Yeah, I can do that. So this, if we look a couple of steps ahead, and I guess in this light, then we see that it is going to help. This is secant tangent minus, like we said, this integral is turning into secant times secant squared minus secant. We can find the antiderivative of individually secant cubed because it's over here. Just like the e to the x cosine x problem, we did that. We have we're going to split this up, or distribute in the parentheses, I guess. Equaling secant cubed. And then we solve for secant cubed. We're going to add to both sides. Add this to both sides. We now have two of these. Equaling secant times tangent. Plus, what's the antiderivative of secant?
Natural log of secant x plus tangent x.
Yeah. Natural log of secant plus tangent. And then we just divide by 2 to solve for the antiderivative of secant. I guess I'll just rewrite it all. Just put it over here like this. So there's the antiderivative for secant cubed. Our problem was 12 secant cubed, so we just multiply everything by 12. You'll have a 6 right here instead of a half. But you can verify that if we went through this process here with the reduction formula number 4 and n equal to 3, right? We get a secant times a tangent over 2 plus this coefficient integral of secant, which is virtually what we ended up with, right? Secant tangent and an integral of secant. So, you know, I guess we work that way just to illustrate that there are sometimes multiple routes you can take. Again, a lot of times it's not obvious. You just got to keep working with it and manipulating it to make sure, you know, it is actually something that works out. Because even just because you can do a step doesn't necessarily mean you should do it, right? And I think that's what makes it difficult is you don't really have any bearings until maybe you're like 4 or 5 steps in and you see, oh, okay, this is going to work. Somebody else would have abandoned it after step 2. But anyhow. Any questions on this example? All right, for powers of tangent and secant, there's 2 ones that we're focusing on. When the n is even, that's the power on secant. So this is for when secant is even, that's the procedure we apply. And when m is odd, m applies to tangent, so tangent is odd. We're going to apply this procedure. If tangent's even and secant's odd, then it says apply, do this, blah, 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 apply reduction formula 4 to each term. So that's something in theory we could do, but since you're not required to remember the reduction formula, you're not going to be dealing with these. So we do not see those.
Is the reduction formula in the homework though?
Maybe. Yeah, it might give it to you. Okay, so we're focusing on powers of secant and tangent when secant is even and tangent is odd. We've got 2 different procedures there. So this example, tangent cubed secant to the 4th, we could actually apply both methods here to see how they play out. So I guess 1, we're going to apply the first one, secant is even. So it says when secant is even, we're going to split off a secant squared. Remember, again, the thing that we split off, we're going to put with our differential. And then that's going to let us know what our substitution should be. So we split off a secant squared when secant is even. We have tangent cubed times secant squared x times secant squared x. Okay. So our u should be what?
Tangent.
Tangent, because the derivative of tangent is secant squared dx. Takes care of this for us. Takes care of this. And then we just need to rewrite secant squared in terms of tangent. So secant squared is what?
1 plus tangent squared?
1 plus tangent squared. So we have the integral of tangent, oh sorry, this is a tangent x cubed. That's going to be our u cubed. We've got 1 times 1 plus tangent squared. So that's times 1 plus u squared. Secant squared x dx, again, that was just du. So like the ones with sine and cosine, you just end up with sort of this polynomial in terms of u. U to the fourth, u to the fifth, antiderivative. And, you know, using either method, what we're going to see is that you do come up with a different antiderivative, but the derivatives are equal to tangent cubed secant to the fourth.
U third.
Oh, u to the third, yeah. I'm not sure why that was. Too busy running my mouth. U to the third.
You were just one step ahead.
Yes.
Yeah.
That's it.
Okay. Where's the space? Yeah. It's right here. So u was tangent. We'll just fill this back in. Tangent over 4 is tangent 6. Secant even, split off a secant squared. The other procedure is if tangent is odd, then we're going to split off a secant times a tangent. Virtually the same procedure as with sines and cosines. It's just depending on which one's even or odd. With secant and tangent, you've got a different thing to split off. So we're splitting off a secant tangent here with our dx. What do we have originally there? Cubed to this tangent cubed secant to the fourth. So we have tangent squared times secant cubed and times our secant tangent that we split off. So that's going to tell us this is our du, virtually our du here. U should be secant because the derivative is secant tangent. That gets all of this. We've got this taken care of as well. We need to rewrite tangent squared now in terms of its Pythagorean identity. So this tangent squared is secant squared minus 1. So we have secant squared minus 1, that's u squared minus 1. Secant cubed, secant tangent dx We got a similar thing here. This one's u to the 5th minus u cubed. The other one was, what was it, similar to that? It was u to the 5th plus u cubed. But our u's are different as well, so. So similar antiderivatives, yet they're different. Secant to the 6th minus over 6 minus secant to the 4th over 4. So you take the derivative of both of those and you apply trig identities, combine them, you should get tangent cubed secant to the 4th. Okay, any questions on this? You just gotta go through these, and you gotta know these procedures for the exam. The other thing to mention is that the textbook doesn't have a strategy for cotangent, cosecant, but if you replace tangent with cotangent and secant with cosecant, the procedure is exactly the same. So just replace this with cotangent everywhere down here too. And this one with cosecant here as well. We did the same procedure. Okay. All right. Try to start that home.